Hi everyone, this is Sai Krishna. This is all about the assignment ICP-6 of a big data. And the task is that what we need to do. We need to use the inbuilt data set of keras model, and we need to add two more layers to the encoder path and the corresponding two layers to decoder path. Run the new model and report your findings. And totally we can say that we need to add four more layers, that are two layers of in the encoder path and two layers of in decoder path. The layers that can be added is conventional 2D, batch norm, conventional 2D transpose, etc. that you will be seeing here. Firstly, we need to import keras model. We need to import keras TensorFlow. From the keras, we need to import convolution 2D model, convolution 2D transpose, input flatten, dense, lambda, and reshape. And from that keras layer itself, we need to import batch normalization, model, MNIST. This is the dataset which we are using for this ICP-8. And we need to import binary cross entropy. And this is the API, and we also need to import a NumPy for the data modeling. We need to model the data before we can try this keras model on that. And we'll be using matplotlib that we'll be using for plotting the visuals of the data. And here we are this MNIST is the, even though it is a supervised data, means it has labels, but we will be removing the labels and we will be using it as unsupervised data. And first of all, we need to check the training and testing data. We will input training and testing data shapes, and yeah, and since the original data is very large, and our GPU cannot tolerate this thing, and we will be reducing the data from 60,000 to 10,000 for the training set, and for testing set we'll be reducing from 10,000 to 1,000 images, and we'll be printing the first 10 images in the training set. These are the 10 images. Let's check the size of the reduced dataset, and we can see the dataset has been reduced. Here, 28 and 28 is the pixel of the every data, pixel of the every picture. You can see this is 28 pixel, this is 28 pixel, length and width. And here we will be modeling the configuration. Model width and model height will be giving those things. And batch size of 128, and number of epochs will be 50. And validation split, the data we'll be using it for the validation is 20% data, and verbosity is 1. And next, we need to reshape the data so that it takes X, like the number of samples in either for testing or training data as an input set. And here we are reshaping the data, passing the numbers. We are converting the data into the floating type, and we are here normalizing the data in by dividing it with 255, because the pixel rate is 255. And now we are creating an encoder model. This is the input. The shape is input shape. We have already given. The name is encoder input. The convolution 2D model with 8 filters. kernel size is 3, strides will be 1, padding same, and we'll be using ReLU function for the activation function. ReLU as the activation function, and we are applying the batch normalization. We'll be applying it here, and again we'll be applying a convolution 2D layer, and again applying convolution 2D layer, and we'll be flattening the data, and we'll be densing the data with the ReLU function. And after that, we will be applying the batch normalization. Let's now take a look into the individual lines of the cover. Here, these two lines, I'll be explaining these things. The next two is mu and sigma are actually not separate from each other. Look at the previous slides. The first outputs are mean values, mu of the encoded input, and second are outputs of the standard deviation, sigma. These we can sample the random variables that constitute the point in latent space onto which one input is mapped. And here we will be printing the convolution shape. Here we are defining the mu and sigma and the batch and the dimensions and the epochs here. Then we use the lambda function to ensure that correct gradients are computed during the backward pass of the values for both sigma and mu. Encoder instantiation. Here we will be using an encoder model. This is the encoder model summary. The total parameters are 5,08,056. Trained parameters are 5,07,904. Non-trained creating the decoder, and we'll be creating the decoder. Creating decoder is a bit simpler, boils down to two-step process: defining it, instantiating it. Our decoder starts with an input layer and decodes input layer. Takes the input with the shape, latent dimensions, which is the vector sample for Z with our encoder. The decode. Next thing we do with instant encode is takes inputs from the decode input layer and outputs whatever is output by the output layer. And this is the decoder summary. Total parameters is 1,79,401. Trainable parameters 1,29,145. Non-trainable parameters 50,256. And here we are creating the new whole VAE. VAE model. If you think the outputs of the entire VAE are the original pass, encoded by the encoder and decoded by the decoder. Comparison and training after compiling. Okay. You can see after using these both layers, encoding and decoding, you can see our model got improved because there's the very less in value loss for this model after using extra 4 layers for this model. And here we will be visualizing the data. Here you can see the 9 is typically, and thank you.